So our third talk of the session will be by Tien from Aarhus University. He'll be talking about precision-guided context sensitivity for pointer analysis.
Okay. Thank you for introduction. Good afternoon, everyone. I'm Tien. Currently, I'm working at Aarhus University, and today I'm going to present our paper, Precision-Guided Context Sensitivity for Pointer Analysis. This is joint work with Yue Li, who is now attending FSC, presenting another of our pointer analysis paper, and Anna Smolar from Aarhus University, and Yanis Maragdakis from University of Athens. In this work, we propose a new pointer analysis technique for OO programs. Pointer analysis is a fundamental static analysis. It determines which objects a variable can point to during runtime. As a fundamental static analysis, pointer analysis is used by many clients and implemented in many analysis tools. So a precise pointer analysis will benefit all these clients and all these tools. It has been demonstrated that context sensitivity is one of the most successful pointer analysis techniques for producing high precision for OO programs. The idea of context sensitivity is to distinguish points to information of the methods by their different calling contexts. Let's take an example. Here, the method foo is called from two call sites with two receiver objects, A1 and A2. In a context-insensitive analysis, variable S will point to S1 and S2, which calls variables B1 and B2 also points both S1 and S2. But these results are imprecise because they contain spurious points to facts. Such imprecision can be avoided by context sensitivity. For example, if we analyze this program in one object sensitivity, then foo will be analyzed in two contexts, A1 and A2. In context A1, S points to S1. In context A2, S points to S2. So as a result, B1 and B2 points to S1 and S2 respectively, which is precise. Now, context sensitivity has been widely adopted in many static analysis frameworks for all programs, such as Java, Android, JavaScript, and so on. But despite its success, context sensitivity comes with heavy efficiency costs. A main reason is that conventional techniques apply CS to all the methods. However, actually, there are many methods do not benefit from context sensitivity. It means that applying CS to this method does not improve precision. But these methods are still analyzed for multiple contexts redundantly, which wastes analysis times. And for the other methods, they can benefit from CS. It means that apply context sensitivity to this method can gain precision. In other words, ignoring context sensitivity for this method will introduce imprecision. And we call this method precision critical methods. Ideally, if we can apply CS to only precision critical methods and context insensitivity to the other methods, then we can preserve the precision of context sensitivity while improve the efficiency of the analysis. To address this problem, so in this work, our goal is to identify precision critical methods. The most important characteristic of this method is that if a pointer analysis applies CI to this method, it will introduce precision losses. But it is still unclear where and how imprecision is introduced in a context-insensitive pointer analysis. In other words, we need to know when a context-sensitive analysis will yield precision benefits, or conversely, when omitting context sensitivity for a method will introduce precision losses. So here comes our first key contribution. In this work, we classify the source of imprecision of the context-insensitive pointer analysis into three general precision loss patterns. We name them direct flow, wrap flow, and unwrapped flow. You will see later that in our experiments, these flows patterns, together with their combinations, account for about 99% of precision in pointer analysis. So we can identify precision critical methods by recognizing these three flow patterns. Now, before we look into these patterns, let me first introduce two simple concepts. We define in and out methods. Given a class, its in methods are the ones who has at least one parameter, and its out methods are the ones whose return type is not while. For example, in this class, in class foo, setf is an in method because it has a parameter p, and getf is an out method because its return type is c, not while. And the methods like setf has parameter, so the object can flow in through its parameter. That's why we call them in method. And for the methods like getf, the object can flow out through its return value. That's why we call them out methods. And according to our definitions, this method bar is neither an in method nor an out method. Now let's look into the three general flow patterns. I will introduce them one by one, and later you will see our technique identify these patterns by leveraging a context-insensitive point analysis as a pre-analysis. We begin with direct flow. If in some execution of the program, object O is passed as a parameter to an in method M1 of class C, then O flows to the return value of an out method M2 of the same class C. Then we say the program has a direct flow from M1 to M2. Here, this red arrow, it means that object flows from variable P to variable R through a series of assignments, fill load store statements, or parameter passing or return value passing through method call or return statements. A typical example of direct flow is the common setter-getter pattern, where the setter method corresponds to the in method and the getter corresponds to the out method. In this example, the objects pointed by P will flow to variable R through a fill store and a fill load. So this is the direct flow. And now it's time to explain our key insight, causes of imprecision. Why this direct flow will introduce imprecision in a context-insensitive pointer analysis? Because when this flow exists in the program, then the objects from different call sites to the same in method will be merged and propagate along the flow to the out methods, and then return together to a different call site to the out method. As a result, the objects will be propagated to the irrelevant places in the program in a CI analysis through these flows. So this is how imprecision is introduced in the CI analysis. Actually, this insight also applies to other precision flow patterns and their combinations. And as you will see later, because the object will also be propagated to the irrelevant places in the CI analysis through other flows. Now let's move to rep flow. If in some execution of the program, the object O is passed as a parameter to in method M1, and then O flows to a store statement, which wraps O into another object W. Here we call it a wrapper object. Then W flows to the return value of an out method M2 of the same class C. Then we say the program has a rep flow from M1 to M2. Unlike direct flow, where flow-in objects and flow-out objects are the same objects, in rep flow, the flow-out object is the wrapper object W, not O. But O is still indirectly propagated to the out method. And here, these red arrows are the same as in the direct flow. They represent object flow through these statements. A typical rep flow, example of the rep flow is collection and iterator. When you assess the elements in a collection, typically the collection wraps its elements into an iterator and then returns the iterators to you. So here, iterator corresponds to the wrapper objects in the rep flow patterns. More generally, the rep flow pattern can also cover the object flow through multiple object wrapping steps. For example, if W is further wrapped into another object W prime, which flows to the out method, then we also say there is a rep flow from M1 to M2 in the program. So this is the rep flow. Finally, unwrapped flow. Actually, this pattern is symmetrical with the rep flow. If an object passes as a parameter to a in method M1 of class C, then O flows to a load statement which unwraps an object U from O. Then U flows to the return value of an out method M2 of the same class C. Then we say there is an unwrapped flow from M1 to M2 in the program. An example of unwrapped flow is the JTK synchronized container, which unwraps the objects from flow-in parameters and return these objects. Similar as the wrapped flow pattern, unwrapped flow pattern also covers the object flows through multiple unwrapping steps. For example, if U is further unwrapped and we get an object U prime, which flows to the return value of the out method, then we also say there is an unwrapped flow from M1 to M2 in the program. So this is the unwrapped flow. In the program, the three general pattern flows can be combined. For example, a flowing object O is further unwrapped, then we get an object U which is wrapped into another object W, and then W flows to the out method. This case is the combination of the unwrapped flow and wrapped flow. And such combinations can also introduce imprecision. Thus, we need to consider the combinations in our analysis. So to prevent object merging and avoid imprecision, we need to identify which methods involved in this flow. Here we say a method is involved in the flow. It means that the method contains at least one statement in these flows. And these methods are precision critical methods that we want to identify because they can introduce imprecision. So if we can identify the precision critical methods and apply CS only to these methods to separate these flows, then we can improve the precision. But note that we need to identify all the methods involved in this flow. Because even we miss one method, then all the relevant objects will be merged at this method and we still lose precision. To achieve all these things, we propose our technique, zipper. You can see this process is like to unzip a zipper, right? So that's why we call our technique zipper. So the next question is, how does zipper analyze flow patterns? I'm not going to discuss this in details. If you have interest, you can read our paper. And generally speaking, we propose a concept, precision flow graph, which can express direct, wrapped, unwrapped flow and their combinations in a uniform way. Concretely, each flow or each combination in the programs can be expressed by a path in the PFG. Note that PFG statically or approximate all the occurrences of the general flows and their combinations in the program. And such our approximation is achieved based on context-insensitive point analysis as pre-analysis. So with PFG, the problem of identifying which methods involved in the flows, namely identifying precision critical methods, can be solved as a simple graph reachability problem on PFG from in methods to the out methods. So this is how zipper identifies precision critical methods. This is overview of our framework. Firstly, we run a fast but imprecise context-insensitive pointer analysis as a pre-analysis, which produced the points to information required by zipper. Then zipper used this information to construct OFG, which is object flow graph for short. You just need to know that OFG is used to help construct PFG. Then zipper built PFGs and solved graph reachability problem on the PFG to identify which methods in this context. Then these methods will be given to a context-sensitive point analysis, which is the main analysis. And this analysis applies context sensitivity to only this method, selected by zipper. We have implemented zipper in Java. Our implementation, its core part is simple and contains only 1,500 lines of code. And we have integrated zipper with dup, which is the state-of-art point analysis frameworks for Java. And zipper can also be easily integrated with other point analysis frameworks. And you can download Zipper and its source code from our website. Now let's see how Zipper performs in practice. Our artifact has been evaluated and it is also available on our website. In the evaluation, the most important research question is that, compared to a conventional context-sensitive analysis, can Zipper-guided analysis preserve precision while improve the efficiency? To answer this question, we choose two-object sensitivity, which is regarded as the most practical high-precision pointer analysis and widely used in both research papers and recent analysis frameworks. So in evaluation, conventional analysis applies 2OBJ to all the methods, and Zipper-guided analysis applies 2OBJ to only the precision-critical methods selected by Zipper. In evaluation, we analyzed 10 large Java programs, including 5 popular real-world applications and 5 dicouple benchmarks. And for dicouple, we exclude 4 small benchmarks where the 2OBJ also runs fast, and the 2 benchmarks where the 2OBJ is not scalable. We use these 4 clients to measure the precision of pointer analysis. All these clients are widely used in pointer analysis research. Now let's see the results. Firstly, Zipper identified 38% of methods as precision-critical methods. So Zipper applies CS to only this method, while conventional analysis applies CS to all the methods. So how about precision? We use conventional analysis as the baseline. So although Zipper applies CS to only 38% of methods, it can achieve 98.8% of precision of the baseline. As a comparison, CI analysis, the precision of CI is only about 60%. So this result shows that these methods identified by Zipper are truly relevant to the precision. It means that Zipper can effectively identify precision-critical methods and preserve the precision. So how about efficiency? We can see Zipper run much faster than conventional analysis. On average, Zipper achieved 3.4 times of speed up compared to conventional analysis. For the best case, the speed up of Zipper is 9 times. This shows that Zipper significantly improved the efficiency of the analysis. So all these results shows that Zipper performs very well in practice and achieves our goal of design. In conclusion, in this work, we propose direct, wrapped, and unwrapped flow, which for the first time clearly explain where and how most imprecision is introduced in context-insensitivity. And we expect that this can also benefit the future research for the static context-sensitive analysis. And then we propose precision flow graph, which concisely model all about flows and their combinations. We implement and release our technique, Zipper, which effectively identifies the precision-critical methods. Our evaluation demonstrates that, in practice, Zipper can preserve essentially all of the precision, while significantly improve the efficiency of pointer analysis. Thank you.
Excellent talk.
Thank you.
Can you go back just one slide back? Yeah. So where are you losing the precision?
We found that it's extremely hard to cover 100% of the precision loss. And we discussed 2 cases of precision loss in our paper. And one case is this parameter outflow cases. So in Zipper, we consider object out only through return value. But for some cases, the object flow in, for this method, object flow in through parameter, and it also flow out through another parameters. So the object flow out through parameter are not considered in our methodology. This is how precision lose. But in Java programs, this case is it's very rare to modify the field of a parameter. So usually in Java, we write code like in this way, which can be captured by the direct flow.
Thank you for the talk. Tae-hoon from Korean University. How the quality of the pre-analysis has an impact on the precision critical methods?
This is an interesting question. In theory, if pre-analysis is more precise, it can help a zipper to identify less precision critical methods. So maybe this can make analysis run faster. But we haven't tried that because the pre-analysis should be fast. So we choose context-insensitive analysis.
There are some other approaches in the past based on dupe also for finding methods that need to be handled context sensitively and or insensitively.
Yes.
So how would this compare with those approaches?
There are
some recent approaches 2-3 years back.
There is a technique called introspective analysis in dupe. It was proposed in PLDI 2014. And actually in our paper, we compared our analysis to introspective analysis. And generally speaking, the precision of our approach is significantly better than the intra-procedure analysis. And also in many cases, our analysis also runs faster than the intra-procedure analysis.
Do they find the same methods or different methods?
We did not check that, but we think the methods are quite different because the precision are quite different.
Thank you. How did you identify the 3 patterns that led to imprecision, and what would I have to do if I want to analyze yet another language? How do I identify the patterns for this language?
You mean for other language? In our technique, we build a PFG, right? And this concept can be generalized. In this graph, the nodes are pointers like variables and fields, which can be generalized to other language. And the edges in this graph are the object flow relations. So this concept can be easily general to other languages. So you can build the similar graph for the other languages to leverage our technique.
Do you expect those languages have the same pattern of imprecision?
It depends on the language. For all languages like C#, we expect that they will be quite similar to these patterns that we identify in our papers. But for C, maybe they will have some differences. But the general idea will be the same because the precision always introduced from the flows that merge. These parts are the same.
I have a question, like how do you prove that the number of methods that Zipper prunes are actually critical?
Sorry?
How do you prove that the methods that the Zipper is pruning are actually critical for context sensitivity?
These are our results. If the methods identified by Zipper is not critical to precision, then it is possible that our Zipper can achieve that close to the conventional one.
Maybe in other words, like if Zipper is not pruning a method or not selecting a method, how do you prove that that method is actually not contributing to the context sensitivity? Maybe I'm asking in more terms of proof.
Oh, you mean the formal proof?
Yeah, it's a heuristic, right? So maybe we can take it offline.
Yeah, sure.
Actually, I have a quick question. So when you talked about your evaluation, you mentioned that you excluded 2 benchmarks from the CAFO because the conventional analysis does not scale to them.
Yeah.
Have you tried your analysis on those 2 benchmarks?
Yes, actually, our Zipper is also unscalable for that 2 benchmarks because the principle of Zipper is to preserve precision. But based on zipper, we can easily develop more heuristic to make trade-off. We have, for example, the bloat benchmark, which this benchmark zipper works not well. For this benchmark, here's the results. These are the analysis time, and these are the 4 precision clients. For all these cases, lower is better. So originally, zipper improved only maybe 20% of the efficiency. But based on zipper, we designed a very simple heuristic. We developed zipper star, which checks flow from an emitter only if its flowing object has too many different types. And this heuristic make analysis run much faster. So this shows that based on zipper, we can easily identify many heuristic to make analysis more scale to the ones which originally cannot be scalable.
Thank our speaker again.
Thank you.